Hello students, Flange here, taking a couple of sections again today of review from Algebra 2 Honors. I is defined as the square root of -1. In this way, we can actually add solutions to quadratic formulas that involve square roots of negative numbers. So the square root of -36 becomes I times the square root of 36, or just plain old 6I. Okay? That's I. And if I is the square root of -1, I squared equals -1. Can you add, subtract, and multiply complex numbers? Well, certainly. It's much like add, subtract, multiplying polynomials, except you have to remember that the I squared is -1. So adding the complex numbers is pretty straightforward. 3 plus 4I plus 2 plus 3I. You add up the real parts and add up the imaginary parts. So you get 5 plus 7I. And similarly with subtracting. Multiplication gets that extra little step in there, because when you multiply complex numbers, 5 plus 3I times 6 minus 3I, you end up doing FOIL, much like you do 5 plus 3x times 6 minus 3x. First would be 30. Outer would be minus 15I. Inner would be 18I. And last would be minus 9I squared. 30 plus 3I minus 9. Now this is where it gets different than FOIL and polynomials. I squared, you have to remember, is -1. So that actually gives you 39 plus 3I. Just for giggles, try this on your TI-89. You'll find that you actually have a button on the TI-89. Look for it. But this is a key idea to remember, that complex conjugates, when you multiply them, you actually get the sum of the squares, a squared plus b squared. So, let's try this. 5 minus 3I divided by 2 plus 7I. We actually have to multiply by the conjugate of the denominator. So 2 minus 7I, or 2 minus 7I. So you can check it on your calculator. And if I erred, let me know. We'll fix it. Okay, what about powers of complex numbers? Well, I to the first is I squared is -1. So I cubed, or I is I squared times I, or -I. I to the fourth is I squared squared. -1 squared is 1. I to the fifth, I to the fourth times I. So you get I. And you see the pattern? And you can really see the pattern if you put it on an Argon diagram, where this is the real axis and this is the imaginary axis, and you have a number out here like 4 plus 3I. But we just did the powers of I. Here was I to the first, and here was I to the second. Here's I cubed. Here's I to the fourth. Here's I to the fifth, and I to the sixth, and I to the seventh, and I to the eighth. And I think you start seeing the pattern. Keep going round and round the circle. And later on we'll talk about more powers of I. And we'll use de Moivre's theorem to expand out things and other things in polar coordinates. Now, Solving quadratic equations by factoring, by completing the square and the quadratic formula, using the discriminant, and losing or gaining a root. Let's make sure we cover most of these ideas. Just get you ready for class. By factoring, this is probably the easiest way to solve quadratics, but it all depends on if you can see it. X squared minus 13x plus 40 equals 0. So x times x will give you the x squared. 40 could be 4 times 10, 2 times 20, or 5 times 8. That's the one we want. And then you set each factor equal to 0, and you get x equals 5, or x equals 8. Now be careful with this, because if I go x minus 3 times 2x plus 1 equals, can I say 9? You can't just set each of these equal to 9. It's the zero product property. So you're basically stuck on this one, and you have to expand it out. 2x squared minus 6x and x is minus 5x minus 3 equals 9. So 2x squared minus 5x minus 12 equals 0. And let's take a look here. What do we get? What factors? 2x times something x. 12 is 4 and 3. 4 and 3 seems to work. 3x and 8x. So if I make it a minus and a plus, we're all set. There you go. X equals negative 3 halves. X equals 4. Now, factoring is a nice technique if it factors. And how do you know if it factors? Well, we'll get to that in a bit here after we look at the discriminant. Completing the square is very handy when you've got an even coefficient on there. And the whole idea is you're completing the square. If I have x squared plus 6x equals 3, I'm trying to complete the square on this x squared plus 6x. Right now, x squared, if you ever did anything with the old, what are they called? Algebra blocks. There's an algebra block that looks like this. It's a big yellow one, and it's x squared. It's an x by x algebra block. And what we're going to do is take the 6x's as 6 of these rectangles that are basically 1 by x rectangles. So each one of these rectangles represents x. And then I actually split it up first. Split it up so that I'm making this square. Instead of just the small x by x square, I want to make an x, essentially an x plus 3 by x plus 3 square. So to complete the square is to fill in these missing parts here. These guys right here. And that's just going to be an array, 3 by 3 is an array of ones. So we're going to add 9 to complete the square. Now, you remember that as the process where you'd go x squared plus 6x plus blank equals 3 plus blank. And what completes the square here is you take half this term, 6 divided by 2, and you get 3, and then square that. So we often say have it and square it. So there you go. Okay, so it's x plus 3 quantity squared on the left. We've completed the square successfully, equals 12. So you take the square root of both sides. And notice this is the absolute value of x plus 3. This simplifies down to 2 root 3, because remember you take the square root of 4 out of there. And so the plus or minus doesn't come from the square root, it comes from the square root of the square here, creating that absolute value, equals plus or minus 2 root 3. So x equals negative 3 plus or minus 2 root 3. So that's completing the square. Now the quadratic formula is used to solve the quadratic equation. And the quadratic equation is ax squared plus bx plus c equals 0. Okay? The quadratic formula solves it for you. And I'm looking for somebody to prove it for us by using completing the square, and that'll be worth big pips. But here goes. If you can't remember, here's the little song. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. That's the last time I'm going to sing for you people. Okay, so you got the quadratic formula down. We'll practice applying it more in class. One of the key things I want to point out here is the discriminant. The discriminant is b squared minus 4ac. And this can basically be used to determine what kind of answers you have then. Because if b squared minus 4ac equals 0, then you get two real double roots. This is, of course, assuming that a, b, and c are real. A lot of our stuff goes out the window if we start using imaginary coefficients in the quadratic formula. But if you use a, b, and c are real coefficients, then you can use this as a predictor. If b squared minus 4ac is greater than 0, then you get two distinct real roots. And if b squared minus 4ac is less than 0, then you get two distinct complex roots, because you're going to be taking the square root of a negative number. Now, a couple of extra little bits on this, and that is, if the discriminant, minus 4ac, equals a perfect square, then you're going to get two rational roots. You could have factored. You could have factored it. And that's what I was talking about before. There's a way you can quickly, if you can want to do the b squared minus 4ac in your head to see if it's a perfect square, that can tell if it's factorable or not. You know, but by that time, you've already figured out b squared minus 4ac, and you've got to have to go work on the quadratic formula done. So, another important application, look at some examples of this in class, is keep this in mind that b squared minus 4ac, setting the discriminant equal to 0 can help you find tangent lines. And that's a big part where we're heading toward in calculus. So make sure you ask about that in class. We're going to do an example of that. For right now, our last page is losing or gaining a root. Do not divide by the unknown. You will lose a root. And a classic example of this is solve x squared minus x equals 0. A lot of kids mistakenly say, ooh, I see the x there, so it's x minus 1 equals 0, x equals 1. Oops, you lost a root. Lost a root. Because you should have said x squared minus x equals 0. X times x minus 1 equals 0. So you get x equals 0 or x equals 1. Okay? Flange out.